Hello everyone, welcome to my class. In today's class, I'm going to cover sections 14.5, the chain rule. Let me start the class right away. First, a quick recall. In Calculus 1, we studied the chain rule for composite functions, the f composite g of t, and the derivative of composite functions is derivative of f composite g with respect to t equals to f prime gt times g prime t. In alternative form, if y is a function of x and x is a function of t, then y becomes a function of t, then we can find the derivative of y with respect to t, which is dy over dt equals to dy over dx times dx over dt. Here on my right hand side is a kind of, we can cancel this dx, then we have dy over dt, which is on my left side. Let's look the diagram on the right hand side. Here y is a function of x and x is a function of t, so y is a function of t, then we can find the derivative of y with respect to t, which is dy over dt equals to dy over dx and then times dx over dt. Great. So the question at this time, we want to ask ourselves, if g is a function of xy and x is a function of t, y is a function of t, then what is the derivative of g with respect to t? Now let's move on. The chain rule is easy to remember with a T diagram. Now in Calculus 3, the chain rule for a function of several variables has several versions. Let's say case 1. Suppose g is a function of xy and x is a function of t and y is a function of t. Let's look on this diagram here, then it's easier for me to explain on this formula. Here z is a function of x and y, it's a two branch, and x is a function of t, single branch, y is a function of t, single branch. Then z will be a function of t, then we can find the derivative of z with respect to t. Now let's go to the formula here. So derivative of z with respect to t equals to, first the partial derivative, because z is a function of x and y, so z partial derivative z with respect to x times the ordinary derivative of x with respect to t, here the left branch. We multiply the left branches, multiply the right branches, and we add them, and then plus del z over del y times dy over dt. Great. Case 2. Suppose z is a function of xy and x is a function of st and y is a function of st. Now let's look the tree diagram. Here z is a function of x and y and x is a function of s and t, y is a function of s and t. So z is a function of s and t, then we can only find the partial derivative of z with respect to s and with respect to t. Then the formula is here. So then this branch here, del z over del s equals to del z over del x times del x over del s, this is the s branch, and on my right side also the s branch, then plus del z over del y times del y over del s. Similarly, the del z over del t equals to del z over del x times del x over del t plus del z over del y times del y over del t. Great. Let's move on. Case 3. Suppose w is a function of x, comma y, comma z, and x is a function of s and t, y is a function of s and t, z is a function of s and t. Then you can find the partial derivative of w with respect to s and with respect to t. Here again we are finding the corresponding branches and add them. So first, partial derivative of w with respect to s equals to partial derivative of w with respect to x times partial derivative of x with respect to s plus partial derivative of w with respect to y times partial derivative of y with respect to s plus partial derivative of w with respect to z times partial derivative of z with respect to s. And similarly, we can find the partial derivative of w with respect to t. Great. Quick remark, we can easily extend the chain rule for a function of 3 or more variables. Now, let's move on. Now, implicit derivatives, finding dy over dx. Here's a quick idea. Define capital Fxy equals to 0, where y equals to little f of x. Again, in the diagram here, capital F is a function of x and y is a function of x. Then by the chain rule, we will get dy over dx equals to negative partial derivative of capital F with respect to x over partial derivative of capital F with respect to y. Similarly, for a function of 3 variables, define capital F of x, y, z equals to 0. Then by the chain rule, we will have partial derivative of z with respect to x equals to minus partial derivative of capital F with respect to x over partial derivative of capital F with respect to z, and partial derivative of z with respect to y equals to minus partial derivative of capital F with respect to y over partial derivative of capital F with respect to z. Great. Now let's do some example. Let's move on. Worked example. Example 1. Find dz over dt for z equals to xy cubed minus x square y, where x equals to sine t and y equals to et. Let's draw the tree diagram. Here z is function of x and y function of t. Then by formula, dz over dt equals to del z over del x times dx over dt plus del z over del y times dy over dt. Here, z is function of 2 variables, so we will take partial derivatives, but x and y are function of single variable t. We will take ordinary calculus on derivatives. Hence, the last step here, dz over dt equals to the partial derivative z with respect to x is y cubed minus 2xy times dx over dt is derivative of sine t is cosine t, plus from formula del z over del y, the partial derivative z with respect to y is 3xy square minus x square times dy dt is exponential t derivative is itself. And keep in mind, when you are taking partial derivatives with respect to x, we keep y constant, and when you take partial derivative with respect to y, we keep x constant. Awesome. Let's move on. Example 2. Find del z over del s and del z over del t for z equals to xy cubed minus x square y, with x equals to s times sine t and y equals to s times et. Let's begin the solutions. Let's look at the tree diagram. Here, z is a function of x and y, and x is a function of st, y is a function of st. So here we can only find the partial derivative of z with respect to s and t. Great. So then the formula is here. So hence, del z over del s equals to the partial derivative of z with respect to x, which is y cubed minus, here is it 2xy times partial derivative of x with respect to s is simply sine t, plus del z over del y, so partial derivative of z with respect to y, taking x constant, is 3xy square minus x square times partial derivative of y with respect to s is simply et. Similarly, we have Another result, del z over del t equals to, it turns out to be y cubed minus 2xy times s times cosine t plus 3xy squared minus x squared times s et. Awesome. Now let's move on. I hope this tree diagram as well as this comparison makes sense to you all. Example 3. Find del w over del s, del w over del t for w equals to xy plus yz plus xz with x equals to s sine t and y equals to s et and z equals to st. Great. Now let's begin the solutions. Let's look at the tree diagram. Here w is a function of x, y, z. X is a function of s and t. Y is a function of s and t. Z is a function of s and t. So we can find the partial derivative of w with respect to s and t. Great. So again, the idea is we find the corresponding branches and then we add them. Awesome. So here is a formula. Then using those formula, our partial derivative of w with respect to s turns out to be here. Let me explain the first one here. Del w over del x means w's partial derivative with respect to x, which is y plus z, is y plus z, and del x over del s, the partial derivative of x with respect to s is simply sine t. Similarly, the second term here, partial derivative w with respect to y is x plus z times partial derivative y with respect to s, simply et. Great. Similarly, the third term, partial derivative w with respect to z, partial derivative w with respect to z is y plus x or x plus y, and times partial derivative z with respect to s, z with respect to s is simply t. Great. Similarly, we will get partial derivative w with respect to t. It turns out to be y plus z times s cosine t plus x plus z times s et plus x plus y times s. Awesome. Great. Now let's move on. Let's do example 4. Suppose that the temperature in a room is modeled by a function of 3 variables, t, which is given to us as 6xyz, and the question is find how fast the rate of change, how fast the temperature changes along the curve helix given by RT equals to cosine t, comma sine t, comma t. That is, x is cosine t, y sine t, and z is t. Great. Let's begin the solutions. Let's draw the tree diagram here. Here is our temperature function. Capital T is dependent on x, y, z, and x, y, z depend on little t. So we can find the regular derivative of capital T with respect to little t. Then here is a formula. Then the next step, so dt over dt equals to, here is a partial derivative of t with respect to x is 6yz times regular derivative of x with respect to t. Here x is cosine t, so derivative of cosine t turns out to be negative sine t. Similarly, middle terms, partial derivative of temperature function with respect to y is 6xz times regular derivative of y with respect to t, or y is sine t, so derivative sine t turns out to be cosine t. Similarly, the third terms, partial derivative of capital T, the temperature function with respect to z is 6xy times regular derivative of z with respect to t, or z is t, so regular derivative of t with respect to t is 1. Simplify, it gives us 6 times negative yz sine t plus xz cosine t plus xy. Quick aside here, for instance, if you want to find the rate of change when time is pi third and xyz is 1, then the rate of change of the temperature turns out to be 3 times 3 minus radical 3. You plug all those values back on these derivatives here. Awesome. Let's do another example, example 5. Implicitly find dy over dx for x squared plus y squared equals to 2xy. Part B, find del z over del x and del z over del y for ez equals to xyz. So part A for function of 2 variables, part B for function of 3 variables. Solutions. First, let's do first part A. So write capital F of xy z equals to, oh, no z here, only f x y equals to x squared plus y squared minus 2x equals to 0. Bring this right hand side to the left side and write to your capital F equals to 0 form. Then by formula, dy over dx turns out to be negative fx over fy. Negative fx is 2x minus 2y over fy is 2y minus 2x. And this cancel out, gives us 1. Similarly, let's do part B. So rewrite capital fxyz equals to 0. That means bring your right hand side to the left side. So this becomes ez minus xyz equals to 0. Then by formula, the partial derivative of z with respect to x is negative fx over fz. Let's take the partial derivative. So this minus as it is. Fx is simply yz over fz's derivative of ez is just ez minus xy. And simplify, this cancel this minus, it turns out to be yz over ez minus xy. Similarly, the partial derivative of z with respect to y turns out to be negative fy over fz equals to xz over ez minus xy. Great. So we finish this example as well as we finish this sections to chain rule. Thank you.